Oops, that's not what I wanted. I hit the wrong record button. Oh, I am recording. Okay. Okay, that's weird. That's why I need to do that. Okay, sure. All right. So, what's wrong?
I said I was going to kill the fly.
Oh, this is always one of my great moments. Is I start off every year talking about the brain and that school is like a big engineering problem because your brain isn't meant to do school. Like at its root level, it was designed to keep you from getting killed. And this is what we call the amygdala is being fired in your brain right now. And that's the reptilian part of you that believes that that bug is going to kill you. And you're having a flight or fight reaction, which means you either want to, right? Your instinct is either to kill it or run away. And no matter how hard I try to keep your attention today, it will win because it fires more of your neurons in a more basic part of your brain than I do, which is interesting. I don't fight biology. I just acknowledge it and go on. All right. So if I go to your Schoology page, I don't know how else to do this other than to just kind of like brute force my way through what's happening here. I'm going to try to like do what's called table checking in computer sciences, which is where in computer science you write a code, okay? So I'm going to go to the practice tab. I'm going to use this. I use a problem from here. And what table checking is you've written a code and you believe that the code is supposed to do what you say it's supposed to do. And then what you do is you pretend to be the computer and walk it through. Does that make sense? So, and see if you get to the same answer that you say you're supposed to get to. And that is, it's an important process, and it's one that people who do like computer programming, software engineers hate to do because it's tedious, right? And it's annoying. So we're going to do it with like a toy problem. But I think by doing the table check here, it kind of highlights and illustrates what's going on behind the scenes. So the first thing is I'm taking problem number 1 from the practice set there, which just says maximize z is x1 plus 2x2 subject to the following constraints. x1 plus 4x2 has to be less than or equal to 8. And x1 plus x2 has to be less than or equal to 12. All variables must be positive. Okay, so this is like the base case. This is what like Simplex likes to operate in and where it wants to operate, okay? The base case is a maximization problem where all of the constraints are less than or equal to. Okay, so what this gives you is a firm bounded region that's feasible, and everything is nice and convex, and you're trying to maximize. So I'm going to solve this like you would in Algebra 2 first. Okay, so this is going to give me x1, x2. And the constraints are, well, x1 is going to be 8, so I need at least 12 here. 5, 6, 7, 8, 9. So 1, 2, 3, 6, 7, 8, I think is there. And then x2 is going to be 2. I need to get up to 12 anyway. So 2, 3, 4, 5, 6, 7, 8. So my first constraint is going to run between those 2 points. Oh, that's ugly. I do this much better at a whiteboard. There we go. Runs between those 2 points and is below it, right? My second constraint is going to run from 12 to 12. This is bothering me. Shoot. That's not an interesting problem. I'm going to change the problem to make it more interesting. I hope you don't mind. Let's throw... Oh, crud. Let's throw 3 there. Can I do that? Is that fair? All right, so if I put a 3 there, then I get a much more interesting problem. This goes to 4 on the x1 and 12 on the x2, right? So that's going to give me that guy, right? So my feasible region is now like this kind of space here, if that makes sense. I know my drawing's not perfect, but I have 4 vertices that I have to contend with. I have this one, that one, and that one are the 4 corners of my feasible region. So this one's easily identified. That's 0, 0. This one's easily identified. That's 0, 2. This one's fairly easily identified, right? Because 12 divided by 3 is 4. So that's going to be 4, 0. So the question is like, where is this one, right? So I have x1 plus 4x2 is equal to 8. I have 3x1 plus 4x2 is equal to 12. Or sorry, no, there's no 4 there. Just x2 is equal to 12, right? So, I don't know, multiply the top one maybe by -3. Gets me -3x1 minus 12x2 is equal to -24. 3x1 plus x2 is equal to 12 is going to make -11.
Is it 12 or is it?
Wait, go ahead.
Is it -12 or if you add?
This line is the same as this line.
Oh, you haven't added them together yet.
I'm adding them, yeah. So I think I should get -11. X2 is -12.
Yeah.
So x2 should be 12 over 11, which isn't all that pretty. But then 3x1 plus 12 over 11 is 12. Ick. I'm going to get a weird answer. That's okay, though. 3x1 is 132. Is that right? 12 times 11. Oh my gosh, math facts. 12 times 10 is 120, right? Another 12, 132, right?
You multiply that
The denominator plus 12 elevenths, right? So this is going to be 144 over 11, I think. Oh, no, it's subtraction. It's subtraction. Stop. You're having trouble with arithmetic, Beam. Why? Stop. Do arithmetic. Oh, there it goes. Hold on. Can I have a wipe? Does that make you happy or does it just gross you out?
Yeah.
Sorry. Thank you. All right, so it's 132 minus 12, right? Is this going to bother you if I have it here?
No.
Okay, good. I'm just trying to be reasonable. So this is going to take me down to 121 over 11, right? Correct, I think? No, 120. Taking away 1/12. Dividing by 3. So I think this makes x1 40 over 11. Are we feeling okay with that? I could always do this. Hold on. Fire it up. Because I'm working way too hard to solve a system of equations when we have an algorithm for that. I'm being dumb. Well, yeah. I just need a bigger computer, I think. I don't know. It's just lots of all working at the same time. I want a computer that will actually compute. How about that? There we go. It's like once it's open, it's not so bad. All right, so let's just check because for some reason my brain is not braining today. 148. And the other one is 3112. Is that what it is? 112. Yeah. Oh, no. It makes it a fraction. Sorry, there we go. 40 over 11 and 12 over 11. Is that what I had? Yes. X1 is the 40 over 11 and 12 over 11. All right, so brain still works. Okay, so this is 40 over 11 and 12 over 11. All right, so if I do this using the other way, I make 0, 0, what were my points? 0, 0, 0, 2, 40 over 11, 12 over 11, and 4, 0. And my function is x1 plus 2x2. Okay, so x1 plus 2x2. So let's go in and do this because this is the way I prefer to do this because I don't have to put it all in. All right, so clear that. All right, and make this 0, 0, 40 over 11, 4, right? And then make this one 0, 2, 12 over 11, 0, and then go L1 plus 2 L2 and store that in L3 and then get my table. So this is going to make this 0, 0 for 5.8182. Sorry, this one's 0. This one's 4, 5.8182. And what was the last one? Still 4? 4. Okay, so my obvious winner is the 5.8182, right? And that's how I would do this by like hand, correct? Okay, so now I'm going to try to table check this. Now that I have a solution, I'm going to try to table check this using simplex, right? So let me set this aside here. And I'm going to do this so that I'm actually going to play with this for a second so that you guys can actually count this as having like completed an actual problem in the problem set, because I don't like the one that's here. So
Do you write the answer as the points or the maximum?
usually the question is like, you want both.
Okay.
You want to know where it is and what it is. Does that make sense? So I'm actually going to de-render that. And I made this a 3, right? In front of there. Is that what I did for the problem?
Yeah.
And then re-rendered it. So there you go. Now yours looks like mine. I fixed it.
Is that like an extension you downloaded?
Yeah, it's a thing called auto latex equations. But I did learn something. I learned that Google actually in Docs has finally caught up to LaTeX. So like if you go into Google Docs, you can now do like insert equation, right? I think, wait a minute, alt insert equation, there it is. And then like you can use like LaTeX stuff. So you can go like pi is equal to frac 2 3 over, whoops, sorry. I lost that, I'm going too fast. 3/2, or which is, it's not, but pi is not 3/2, but make it 22 over 7. It'll feel better. So you can actually do LaTeX inside of Google right now, which makes it worth learning LaTeX. The problem that I don't like about it is that like it doesn't feel like it's sizing to the right size that I want. I don't have a whole, I still like the other editor, but Google finally is catching up to where I am. But it came out in a recent iteration that you can use LaTeX inside of Google now. So anyway, Google LaTeX, it's actually spelled capital A, capital L, little a, big T, little e, big X. It's pronounced LaTeX, not latex. Okay, so there you go. But it's how the rest of the scientific community communicates symbols. So learning it's not a bad idea. It's a typesetting language is the basic idea. All right, so that's stats. Let's not do stats. Let's bring up your stuff here. And let's look at how would we build the table for this, right? So the table kind of plays out this way, right? So we're going to get 2 rows. You're going to get 1, 4, right? 3, 1. And then you get like 1, 0, 0, 1. Does that make sense what I've done there? This is building for simplex. Okay, so this is your constraints. So you have an x1 and x2. Okay, and then what it's equal to comes out here, 8, 12. Okay, so that's your guy. So that's the end. And then what you have here is what are going to be called S1 and S2. Okay, we have to introduce 2 slack variables. So what you're doing is you're turning an inequality into an equation by introducing a variable. So this x1, let me kind of write it up here, x1 plus 4x2 could be seen as equal to 8 for some value of s1. So we're making an arbitrary slack variable there. Likewise, 3x1 plus x2 plus some other slack variable is going to make that equal to 12. That's what's going to allow us to make pivots. Okay. So down here, what we do is we put the objective function. So this is going to be a -1. you make them negatives. So this is really weird, but the objective function actually comes out as negative values down here, or the game doesn't work. And then you just fill in everything else with zeros. Okay. I have to check something really quick because I don't want to teach doo-doo. It's important for me to teach stuff that's not wrong. I don't do this often by hand, and I want to make sure that I have the ratios right. ACalc linear. Let's just do simplex. There we go. It's B over, okay, so it's the over that. Okay, and I want the smallest of those. Got it. Okay, so sorry about that. Just not wanting to get it wrong. Where's the, it's going to be next to this. There we go. All right. So what I do when I'm pivoting using simplex is I first start at looking at the column and I find the most negative column, right? And then I look and I do some division here. So it's, I take this column, that's what I'm going to use as my column. And then I got to figure out which row. So currently this is the X1 row. This is the X2 row. Sorry, that's not correct. Give me a moment. What did I call them on here? No, not X1 and X2. S2, that's why. My brain's wrong. S1 and S2. The slack, each, you get a slack row for each of them. Okay, so that being said, what I got to do is I have to figure out which row I'm going to use. So I take this number at the end, the 8, and divide it by the number in the middle there is 2. And then I take the 12 and divide it by the number in the middle there, which is 1, gets me 12. And I pick the one of those that's actually the smallest. Okay, so which one's smaller, 2 or 12? 2. Okay, so that's going to say I'm going to pivot on this point, the 4. Okay, now thinking about my earlier drawing a little bit here, what I have going on here is I had these two constraints in there. This one went 8 here to 4 here, or 2 here, right? So there was that constraint. And then the other constraint is running between 4 and 12, right? So it went this way. And what I'm doing is I'm starting currently at 0, 0, okay? So right now my algorithm is at 0, 0. And the reason why I know this is that neither X1 nor X2 are on the left here. So their current values are not in the game, so they are both 0. And down here, I'm reading the value 0, because that's where I am at that the objective function is equal to 0 at that point. So what I want to do is I want to make that 4 into a 1. Okay, so when I'm pivoting, what's going to happen is I'm going to first, this X2 and this S1 are going to exchange places. I'll get to that in a minute. But that 4 I want to be as a 1. So I divide the whole row by 4. So I'm going to get a 4th. I'm going to get 1. I'm going to get a 4th, a 0, and a 2. Okay? Now, what I want then is everything else in this column, I want that to be a 0. So using like row operations, I need to multiply, well, what I just did here by -1 and add it to that. So you're never going to have to do this by hand, okay? Not for me, you won't, okay? So this I want to be a 0, so I'm going to multiply this by -1 and add it to that. So that's going to make that a 0. -1/4 from 12/4 is, I think, 11/4, right? This becomes negative a fourth. This stays as 1. Negative 2 plus 12 is 10. Is that right? Yeah, negative 2 plus 12 is 10. So that's good. And then I make the pivot on the second row here, which is going to be, let's see, I have to multiply this by negative 2. So negative 2, my brain's not having fun with this. I have to multiply by 2. So 2 times, or 2 divided by 4, there we go, divide by 4 minus 1 lands me at negative 1/2. This is going to be 0. This is going to be negative 1/2. This is still going to be 0. 8 times negative 2. Sorry, 8 times 2. That's not right. Stop. One-fourth times 2 is just a half. There we go. That's better. That one stays at 0. 2 times 2 is 4 plus 0 is 4. Okay, so what just happened here is I made a pivot. I exchanged the x2 for the s1. So this is going to become x2. This stays s2. These stay labeled as x1, x2, s1, s2. But now if I read my chart, what just happened here is I've moved from the point 0, 0 with a value of 0, but now x2 just became 2. Does that make sense? So this is now the point 0, 2, and I read the value down here leads to a value of 4. So what I just did is I went along the edge here and landed at that corner through one pivot. Now, looking back at my answers from the earlier part, that means I went from here to here on the table. You see it? So that's what this thing is doing, is it's climbing around the corners, but it's doing it in such a way that it's making the most efficient move possible. Okay? So now I look at the bottom row and I say, what's the most negative number? That's here. So this is now the column in question. Okay? So I have to divide. I have to divide 2 by a fourth. 2 divided by 1/4 is 8. 10 divided by 4/11 is 40 over 11, which is 40 divided by 11 is 3.63. So which one of those is smaller, 8 or 3.63? So I'm going to pivot on this row, okay? Which seems nuts, but that's okay. So let's look at the table that I end up with here. This row is not changing. Or no, it will change. Sorry, that's not correct. This row, I need to change from X. So I'm going to pivot from S2 to X1. All right, so there we go. And all right, so I need a 1 here. So this has got to be a 1, which means I have to multiply by 4/11. So that's 0. This is going to be negative 11. And no, 4/11 times negative 1/4 is going to be negative 1/11. There we go. And then this is going to become 4/11. And 10 times 4/11 is 40 over 11. Correct? That number should look familiar, oddly. Okay, so what happens when I apply this here? Well, x2, I want a 0 here, right? So I'm going to multiply this row by negative 1/4 and add. So multiply by negative 1/4 and add. So that gives me a 0. That's going to stay 1. All right, so negative 1/4 times negative 1/11, right, plus 1/4 is that number, whatever that is. That's 3/11. Okay, so this is going to be 3/11. Negative 1/4 times 4/11 is negative 1/11. So that's going to go there. And then negative 1/4 times, oops, 40/11 plus 2. Delete. Gives me that, which is, lo and behold, 12/11. Ha, fascinating, right? So what do we got here? We have this has to go to, so I need to make this 0, right? So I need to multiply this by 1/2 and add, right? So 0, 0. Negative 1/11 times 1/2 is negative 1/22 plus a half. Okay, so let's figure out what that would be. Negative 1/22 plus 1/2 gives me, what is that? 5/11. And then I have to take negative 4/11 plus 1/2, no, times 1/2. How about divide by times, I need parentheses here. Let's fix that. 4/11 times 1/2. There we go. And that's just going to be plus 0. So that's just going to come out as, what is that? 2/11. And then one last one here. 0.5 times 40/11 plus 4 gives me 64/11. Is that what I should get? Oh, 5.818, right, is 64/11, 5.818. Yeah, there it is. So that's going to give me the same number, 5.818. All right, so what just happened here? Well, x1 changed from that location to 40/11, and the x2 changed likewise to 12/11, which it landed me here at 12/11, 40/11, and got me there. And what happens when I get to the end of the problem is all of these go positive. So there's no negative column to start with. Does that make sense? So that means I have found the optimal point. And then I just read the table. X1 is 40/11. X2 is 12/11. And Z is 64/11. Okay. Now, that means that this just did the exact same thing, but did it using matrix pivoting rather than linear programming. Does that make sense? Okay, so what I want to have happen now that I've table checked it is if the algorithm in the computer is running correctly, it should do this. So Thank you. All right, so clear, get it all out, CLC. All right, so this is where we started the pivoting, right? So when I formed this table, this is the table I want to pivot from, right? So my A part is the block. So let me do this. Let's actually walk through just forming the table one more time because that's worth doing. All right, so remember that the table gets formed this way. It's got 4 parts, right? The A part should be from the constraints. 1, 4, and then I get 1, 0, 8. And then 3, 1, 0, 1, 12. So like, if you kind of look at it, this is going to be the coefficients from your constraints, and then this is going to be ones down the diagonal, 0 everywhere else. Does that make sense? This is the A part of the matrix. This is the B part of the matrix. And then I get these from here, -1, -2, 0, 0, 0. So this is A. This is B. This is C. Okay? So now I go into MATLAB and I say, okay, great wonder of the universe. Make A 1, 4, 1, 0, and then 3, 1, 0, 1, right? There's A. Make B, and I think you can just put it in sideways, 8, 12. I think it'll figure it out. And C being -1, -2, 0, 0. And then I go NMA simplex, A, B, C, false, because I don't want to see all the matrices in between, right? And I hit enter. Oops. Oh, capital A. That's why it didn't like me. There we go. And if you look, I'm going to rats the answer just so you can see that it's the same. But if you look, that's the final matrix that I pivoted to. It came to the exact same spot. So where do you read the answer, right? That's the big question. And how do you read the answer? All right, so let's look at what this matrix actually says. So I'm going to kind of rebuild this in print here. So you have on the left part, you're getting 0, 1, 1, 0, 0, 0, right? And then I have 3, 11, -1, 11, 5, 11, -1, 11, 4, 11, 2, 11, and then 12 elevenths, 40 elevenths, 64 elevenths, right? You can write these in decimals. I don't care. But if I kind of put in the bars, that's where they are, right? So, yeah. Can I see? Because there's probably something that's goofy. Okay, can I see? Can I back up? Let me go. I see your A. Okay, that's what it's using as A. So A's not right.
That's so weird.
Maybe yeah.
It's an A from like the last time I did something, because I could have swore I typed in the.
It's.
Oh, I just have 2 A's, I guess.
Okay. Oh, so that's the A. Okay, so there's A.
Yeah.
1, 4. Okay, and B is 8, 12, right? And C is that. And then you did this. Oops, sorry. And you got that.
Yes.
Which is really weird that you're not getting the same thing I am. Let me look at A one more time. Let me look at my A. All right. 14103.101. We agree with that, right?
Mhm.
B is 812. And you have B being 812. And C, -2.
Okay.
There it is. There it is. There it is. Okay, math still works. That's good. Always fun. All right, so how do I read this? So remember, this is always going to be x1, x2, s1, s2, right? Look for the non-noisy rows, right? This tells me that 1 tells me that x2 is this value. Does that make sense? This tells me that x1 is this value. And this tells me that z is that value. Okay. Now, I started this off with acknowledging that table checking is tedious, right? Which you just observed. It's tedious and not fun. When do you table check in computer sciences? Is when the thing doesn't go right, correct? That's when you end up in that position. So let's work the second problem here, because now when you're looking at problem 2 here, there's no way in heck you're going to do that problem by hand. Like, can you graph in 3 dimensions and find all the intersections? I mean, if I gave you enough time and enough crayons, you probably could pull it off, but it doesn't sound like a lot of fun to me, right? So let's kind of layer in things here. A is not so hard to come up with here, right? It's just reading off the constraints. Let me build the matrix. Let's actually just build it and then put it in. That makes more sense to me. Don't make leaps. Leaps are bad. Leaps confuse people. All right, so building the initial tableau or initial matrix is the hard part, right? So you have 2, -1, 1. Now, how many constraints do I have here? Don't count the last one. Don't count the positivity one. 3, right? So I'm going to need 1, 0, 0, right? All right, and the B here is 42. So the second row should read 2, 3, -1, 0, 1, 0. Why is this -1? Or -4. Oops, thank you. -4. Okay, we're good. And then 6, -1, 3, 0, 0, 1, also 42, right? All right, so that handles that part of the matrix. And then down here, I end up with the -5, -2, -8. And that's the part that everybody misses, is to make those negative. The algorithm won't work if they're positive. Okay. 0, 0, 0, 0. Okay. So if you get good enough at this, you don't have to make that step in writing, but sometimes it helps. 1, 1, 0, 0, 2, 3, -1, 0, 1, 0, 6, -1, 3, 0, 0, 1. Okay, so there's A. B is just 3 42s. That's nice. And C is the last row, but not the last 0, right? So it's -5, -2, -8, 0, 0, 0. And then I do the NMA simplex. And let me do it with the full screen open. There we go. It fit to my screen is what it did. So I have the answer, right? So where does this maximize? Let's get that piece of paper over here. So let's look. Yeah. So the maximization, the first one All right, so let's take a look. This would be the x1 row. So x1 is still 0, isn't it? It's a noisy row. So x1 is 0 here. This is the x2 row, right? Or x2 column. With me there?
I'm just confused how x1 is 0.
What's that?
I'm just confused how x1 is 0.
Because it is. Yeah, optimizing it says don't do any of x1.
Okay.
Yeah. x2 is actually here, which is at 21. So at x2, you make 21. x3 is this one, right? It lines up with 21 also, correct? And z is that number down in the corner, 210. So my solution is don't make any x1s, make 21 x2s, make 21 x3s, and you will yield 210, and you can't get any better. Now, take a look at the original problem, and let's see if it fits the constraints. So negative 4x2, so negative 4 times 21 plus 21 would be 42, exactly, right? So I've met that constraint. 3 times 21 minus 21 is exactly 42, meets that constraint. Negative 21 plus 3 times 21 hits 42 exactly, that constraint. And given those options, the best actual option is to not build any x1s and split it evenly between the x2 and the x3. Now, that's powerful because I've just did this with 3 variables. How many variables can I do this for? Any finite number. So I can have any finite number of constraints with any finite number of variables in a linear objective function. And it's a maximization problem with minimizing constraints, and this will solve it. And it solves it in what's called polynomial time, which means that even if it's a really, really huge system, the computer goes blink and it has the answer. It's an extremely efficient system because it just goes along the edge of this thing until it finds the right one and then it stops. Now, admittedly, they've never actually proven that it works in polynomial time. This is an interesting thing. They've never found a case where it gets worse. So polynomial time means this. For every input, linear time, ON, is for every input, there's some multiple of that input operations that have to happen in order to get an answer, okay? ONP, which is polynomial time, means that there's some polynomial times that input operations to get an answer. That's still relatively fast. The one that's bad is exponential time. Okay, so you put in something and you have an exponential number of operations to get that answer. That's going really slow. That's bad when you have a computer program, okay? Where is this used? This is how Amazon figures out how to get your package to you. This is the algorithm. Okay, the mystical Jeff Bezos algorithm. This is it. It's not a mystery. He just applied it to logistics, international logistics, and figured out how to make that happen. Now, real world, Amazon started off as what kind of company? This is a great question. What did Amazon do originally? Nope. College textbooks. So when I was in college, you would go to the college bookstore and buy all your books and go, okay, I have them all. So the college bookstores became monopolies because they were the only place that you were buying your college bookstore. So you'd pay these inflated prices on textbooks. So what Bezos did is he said, there's all these bookstores across the country. why just have you order your books from the local bookstore? So internet was coming into reality around that time. And you say, okay, what book do you want? I will find the bookstore that has that book, and all of these sellers want to be in my marketplace because they want to sell their books. I will find that book much cheaper than your store will, and I will get it to you before the semester starts. You'll have it on time for the first day of classes. And that's where it started. And then he figured out, if I can do that for college textbooks, I can do it for anything. And now you have Amazon. But this is how he figured out the textbook problem, and then he just scaled it up. Now, the problem is that he's ahead of any of you to be his competitor. He's got the path. You would never be able to take him over, because in order to catch up to where he is, it's like the tortoise and Achilles. You'll never catch up. You don't have enough time. You'll die before you catch him. So try another idea before you make your billions, okay? But that's how he did it. So this is the algorithm that drives Amazon and a lot of other things. So play around with them, feed the things in, get your answers out. I will never make you do them by hand because it's painful. And neither does Jeff Bezos do these by hand, okay? But knowing that there is a method behind it is probably a good idea. Okay? All right, enjoy Ring, stay warm. It's cold. So what do we think? Snow tomorrow?
I don't know.
I don't know.
Class really just doesn't go intended to be experientially important, so make sure you're in class. So I guess I'm going to dance.
All I